We're going to prove a beautiful theorem in introductory field theory from first principles. I'm going to give you a lot of intuition. If F is a finite field, I'll explain what that is. Okay, we'll talk through all of this very clearly. Then the cardinality of F, the number of elements in F, is the power of some prime number. And this is going to be a beautiful introduction to give you a deep intuition of finite fields. Okay, we're going to talk about a lot of fundamental concepts along the way. So let's just dive into it and think about what's going on. And in math, it always helps to just think about things from first principles. So what is a field, first of all? I'm just going to give a brief review. I assume you are familiar with this. But it's a structure where you have an addition and a multiplication and a subtraction, which is the inverse of addition, and a division, which is the inverse of a multiplication. You can divide by any element that's non-zero. And for 0, we basically have with addition what's called an additive identity 0. So anything plus 0 is that thing, and a multiplicative identity 1. Anything times 1 is that thing. And so you have this structure. You have addition and multiplication. So of course, standard examples are the rational numbers are a field. You can divide, add, subtract, multiply, real numbers, complex numbers. You also want laws like associativity, distributivity, or multiplication with respect to addition, just the standard laws of arithmetic to be true. On the other hand, Z is not a field because you can't divide. Within Z, you can't get, dividing 3 by 2 is not an integer anymore. So that's an example. But we have finite fields in this video, and finite fields are really beautiful structures because the finiteness really constrains what they are. And we're going to play around with this, okay? We're going to play around with this. So we're going to start off with our finite field F, and we're going to think about 1, okay? And this is going to be very interesting because we're going to start off by adding 1 to itself, just adding, keep adding 1 to itself 2 times, 1 to itself 3 times. Sometimes people like to write this as, this is 2. This is what you call 2 in the field. This is what you call 3 in the field. But you have to be careful because it's not really the integers, it's just some field. But the interesting thing is in a finite field, right? In these fields we studied here, you get all the natural numbers, basically, if you think about them in here. But in a finite field, what happens? I mean, you can't get an infinite set because the field is finite, right? So there has to be a repetition somewhere. There has to be a repetition somewhere. And what that means is that for some n and m, adding 1 to itself n times, okay? Adding 1 to itself n times has to be the same as adding 1 to itself m times, right? For some n and m, where you can say that m is going to be less than n. Okay, so you could say n is greater than m. Okay, so distinct n and m. There has to be some repetition, otherwise you'd have an infinite set in a finite field, which is impossible. But now what you can do is you can use the field axioms, the addition axioms. You can subtract the right-hand side from both sides. Okay, so you can subtract adding 1 to itself m times. You can subtract that off from both sides, so adding 1 to itself m times here. And what that gives you is that adding 1 to itself n minus m times, right? N minus m times is going to equal to 0. So that shows you in a finite field this curious property that it has to eventually become 0. It's very cool. 1 plus 1 plus 1 eventually has to become 0. Otherwise, you can't have a finite set structure. We're going to now study this. We're going to use this. It's going to be a crucial property to get the prime power order for the field. Number of elements in the field is a prime power order. So where does the prime come in? That's the next step. And if you're enjoying my content so far, making hard math very accessible. I'm not assuming you know a lot of stuff. I'm doing everything from scratch to make it very clear. Please don't forget to like and hype if the video has been uploaded in the last 7 days. And subscribe for so much fun math content. I've got an entire playlist of abstract algebra, all topics, topology, real analysis, everything. So you don't want to miss all of that. And let's just get into the video now. And let's now understand where the prime comes in. So we know that adding 1 to itself some number of times is 0. There's going to be a smallest such number. Okay, so there's going to be a smallest such number, 1 plus dot 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 plus 1, let's say k times. There's going to be a smallest k, so that's going to equal to 0, where k is smallest. Okay, this is the well-ordering principle. Okay, if you're trying to think about it rigorously, it's a well-ordering principle for the natural numbers. Any non-empty set has a minimum element. So there's some natural number where adding 1 to itself that many times is 0. So there's a smallest such natural number. And we call k the characteristic of f. Okay, we call A the k of the characteristic of f. And actually, I'm going to be suggestive here. And as you can see, I replaced the k with p, which suggests something that actually this characteristic is a prime number. And why is that? Well, it's a very nice slick proof, okay? And we're going to use, we so far used the multiplicative structure because we've used the multiplicative identity one, but we haven't really multiplied anything. Let's now start multiplying. So what we're going to do is we're going to say that why is p prime? Well, it's a proof by contradiction, okay? The proof by contradiction is assume that p is equal to a times b, okay? Where let's say that a, b are both less than p, okay? So this is what we're doing, okay? Assume that it's not prime, okay? Now if we assume it's not prime, we can observe that 1 plus dot 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 plus 1 p times, so I'm going to write this as follows, p times, that is going to equal to 1 plus 1 dot dot dot, so we're going to write this as 1 plus dot 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 plus 1 a times, and 1 plus dot 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 plus 1 b times. And the reason is using the field axiom. So we have to be very careful, we're not colluding things. So this is a decomposition in the natural numbers. We're not dealing with the field. Here we're dealing with the field. But if you think about 1 is a multiplicative identity and using the distributive law of multiplication with respect to addition, 1 times 1 is 1, you can collude this to get AB ones, which is just P ones because P is AB, but that's 0. And we know that P is the smallest number, so that 1 plus 1 dot dot dot, P times is going to equal to 0. So therefore, neither of these are 0, but a product of two non-zero things cannot be 0. That's what it's called an integral domain. Fields are integral domains because of division. So you can divide, you can divide both sides by 1 plus 1 dot 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 a times. And if you do that, you're going to get 1 plus dot 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 plus 1 b times is 0, which is a contradiction of the minimality of P. So for example, Z is an integral domain, but it's not a field, okay? So you can't divide, but it's still the case that AB is 0 implies A is 0 or B is 0. There are no zero divisors, so to speak. So now we know the characteristic is prime, and this is going to give us some structure on F that's going to allow us to prove this, okay? And let's just get into that now. By the way, if the field is something like the rational numbers, real numbers, or complex numbers, we say it as characteristic 0. There is no smallest k, so that 1 plus dot 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 plus 1 k times is 0. So then we say the characteristic is 0. It's interesting that there is a characteristic for every field, and if it's non-zero, it has to be prime. This argument shows that. We didn't assume the finiteness here. But there are infinite fields of prime non-zero characteristic, okay? You can have that. So let's now get into how to show this, that the number of elements in F is a prime power. We now have understood, we can define this thing inside F. We're going to call it Fp to be suggestive, and what it is 0, 1, 2, dot, 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 p minus 1, okay? So what this really means, as I'm just sort of using the notation I explained earlier, we're thinking of 2 as 1 plus 1, and we're thinking of p minus 1 as 1 plus 1 p minus 1 times, okay? And we know that because the characteristic is p, if you add another 1, you get 0. So these cycles, this structure is what is called a subfield of F. And this is what is just modular arithmetic, okay? This is like the natural numbers modulo p are up to isomorphism, okay? So I'm not going to get into that, but essentially within F you have this structure, which we know, okay? It's modular arithmetic, and Fp is contained in F. You can multiply and add, sums of ones and get other sums of ones, so it's a closed system. But what's important here is this gives the structure of F, the structure of a vector space over Fp. And I'm explaining everything from first principles to intuitively see why this is true. I'm not hiding behind a bunch of theorems. That's how I'm trying to explain this math to you. So what is important here is when you think of vector spaces, you only care about addition for vectors, okay? You don't think about multiplying vectors. I mean, there's no real multiplicative structure in general. Sometimes in certain dimensions you have some pseudo structures like cross products or whatever. They're not real multiplications, so you can't divide, etc. But we think about the additive structure of F, and you can add vectors, and we're going to be able to scale vectors by Fp. So Fp is contained in F. So when I say scaling vectors in F, elements of F, I'm thinking of vectors. I'm scaling them by elements of Fp. I'm thinking of multiplication in F by viewing an element of Fp, which I'm thinking of as a scalar, and an element of F, which I'm thinking of as a vector, and that scalar times the vector is just multiplication in F. Okay? And it's a very interesting multiplication because remember, elements of Fp are just sums of ones. So really, if you add a bunch of ones and you multiply with an element of F, let's call it V, so we think of this as being in Fp and we think of this as being in F, you can think of that product as basically just being V plus dot 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 plus V, whatever number of times, okay? So you're basically using the additive structure of F, but you're thinking of it as a vector space over Fp, and that gives us a conceptual basis for understanding what's happening here, and I'm going to do that from first principles. So I'm going to give you two ways of looking at it, the quick way and also getting into it kind of way from first principles. So basically, knowing that F is a finite field, it has to be a finite dimensional vector space over Fp. Okay, so it's a finite dimensional vector space over Fp. So we can think of it as an n-dimensional vector space for some n. Okay, so we can say that the dimension of F over Fp. Okay, so F as an Fp vector space. Okay, you can write it in this way. This dimension is n, it's finite. Sometimes, you can think of this, another sort of concept from field theory, you can think of this as a field extension, because Fp is contained in F, then the degree of the field extension is basically the dimension of F as an Fp vector space. That's another definition. Since it's finite, we know that we can think of F as isomorphic by vector space theory. We know that it's isomorphic to a finite dimensional vector space over Fp of dimension n. We can think of it as Fp to the n. Once you fix the basis of n vectors, you can think of it as Fp to the n. So you have n coordinates, okay? So Fp times Fp times Fp dot 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 n times. And when you think of it that way, you can see that, there's just going to be p to the n elements, okay? So therefore, the cardinality of F is going to be p to the n. Now, what I don't like about this argument is it maybe kind of obscures something. So I want to just give you a little bit. It's a nice conceptual argument. I just want to give you a little bit of an extra, because this uses, the theory that every vector space has a basis uses the axiom of choice. But we don't need the axiom of choice in this case. And we can give a very direct proof because everything is finite. It's very concrete. I'm just going to show that to you so you can really visualize. It's going to give you a deeper understanding. So we can actually see why F has p to the n elements as follows. So what you can do is you can first take a non-zero. So you have F. You first take a non-zero element of F. Okay, so pick V1. V1 is non-zero, V1 is in F. Okay, now what we can do is we can look at the span of V1. Everything is thinking of F as a vector space over Fp. So we can look at the span of V1. This is all the multiples of V1 by elements of Fp, which you can nicely think of as just adding V to itself some number of times. Because scaling V by 1 plus dot 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 plus 1 some number of times is adding V to itself some number of times. So you can see V plus V dot dot dot, V plus dot 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 plus V. And you can sort of see that that's just, the last term, the last term is just p minus 1. 1 plus dot 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 plus 1, p minus 1 times V. Okay, for example. So that's the span of V1. If that is F, then we've seen that F has p elements. F is dimension 1 over Fp. We've constructed a basis of F. Now we're going to keep going with this construction. So assuming that span of V1 is not equal to F, assuming span of V1 is not equal to F, you can then conclude that you can pick V2 outside of the span of V1 in F, okay? And then you can look at the span of V1 and V2. So the span of V1 and V2, so you look at the span of V1, V2, I'm just going to write this now more specifically as A1, V1 plus A2, V2. All the combinations where A1, A2 are in Fp. Okay, so this is how you sort of try to construct a basis of any vector space. So you can keep going with this and you can say that once I picked Vi minus 1, once I pick V1 dot 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 Vi minus 1, I can pick Vi assuming that the span of these, assuming that the span of V1 dot 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 Vi minus 1 is not equal to F, I can pick Vi outside of that span. Okay, I can pick outside of that span V1 up to Vi minus 1, and this process has to terminate because F is finite. Okay, so that's a cool thing. We're dealing with finite fields. You can be very explicit about this basis. That process has to terminate, and because that process terminates, we know that there's going to be some V1 up to Vn that, as we've constructed, that span F. Okay, so at the end of the process up to some n, we know that the span of V1 up to Vn is equal to F. And now you can actually see that they have to be linearly independent. And I want to point out why this doesn't use the axiom of choice. It doesn't use the axiom of choice because when you're dealing with the axiom of choice, you have to pick something from a bunch of sets. You don't have a formula or an algorithm for picking it. But when you have finite sets like F, you can index, you can label all the elements of F as you can label them as, like, let's just say, for example, L1 dot 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 LM. Okay, you can label them. You can make a choice. You can just choose the V2 that is the minimum index, L minimum index that is outside the span of V1. So if you know there is a possibility, it's a non-empty set, you can choose the index, let's say I, so that Li, minimum index I, so that Li is outside the the span of V1 and then call that V2. So that gives you a formula algorithm for making the choices. So no axiom of choice required there. And once you've done this, you know that they're going to be a basis for F. You know it's going to be a basis of F because what you can do is you can say that if they were linearly independent, if C1, V1 up to, let's say, Cn, Vn was equal to 0, and we know that not all the Ci's are 0, okay, in this relation. We're assuming that not all the Ci's are 0. What you can do is you can choose the I maximal. So choose I max such that Ci is non-zero. Okay, so then, because all the latest Cj's will be 0 for j greater than I, we can write this as C1 V1 dot 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 Ci Vi is going to equal to 0. And then you can, because Ci is non-zero, you can put everything to one side. You can put all the C1 V1 up to Ci minus 1 Vi minus 1 to the other side. You can write Ci Vi is equal to negative C1 V1 negative C2 V2 dot 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 negative Ci minus 1 Vi minus 1. And therefore you can write Vi as a linear combination of V1 through Vi minus 1, which is a contradiction. You divide by Ci. Okay, we're using the field axioms. You divide by Ci and you go on, you get negative Ci minus 1 divided by Ci times Vi minus 1 using the field axioms, and that contradicts the choice that each Vi was chosen outside the span of its predecessors. So that shows that, you know, this is the basis. Every element of F is uniquely a combination of V1 through Vn. So therefore, you know, you can think of it as Fp to the n. You can think of the C1 up to Cn as coordinates, and there's going to be p to the n elements in F. Hope you love that explanation, and it's really cool because there's actually a unique field up to isomorphism with p to the n elements for each prime p and each natural number n. The unique field, that means the multiplicative structure is determined too, and we really didn't use the multiplicative structure all that much in this video. As I said, scalar multiplication by elements of Fp was basically just adding something to itself some number of times. So we're not using the multiplicative structure there, but we did use it to show the characteristic was a prime number, to therefore show that it's p to the n for some prime p as a number of elements of F. I've got two fun videos for you. Really gonna love these videos. The first is a similar thing to this, that if you have a group that has a unique maximal subgroup, that means a biggest subgroup, not all of the group, but a biggest subgroup that every subgroup of the group is contained in that, except the whole group of course, then the number of elements in the group, if it's finite, has to be the power of a prime number. And it's a completely different argument. It's so fun. Group theory really drains in that abstract algebra for you, really helps you to understand that. Check it out. It's going to pop up on the screen here. Here's a super cool video for you. R, the real numbers, is a vector space over the rational numbers. Just like in this video, because the rational numbers are contained in the real numbers, we can scale real numbers by rational numbers. But there is a proof using prime numbers and properties of prime numbers to show that R is infinite dimensional as a Q vector space. You're going to love it. Check it out. It's going to pop up on the screen here.